In our next example, we've got a retail store that estimates that its weekly sales S and weekly advertising costs X, which are both measured in dollars, are related by the function S equals 50,000 minus 20,000 times e to the negative 0.00004x. The store is currently spending $2,000 per week and decides to increase its advertising budget by $300 per week. I would like to know what will be the impact of this increase on sales, or in other words, I want to find the rate of change of sales. So if you haven't done so already, I would recommend that you pause the video and try the first 3 steps or so on your own. I don't think a picture will be particularly helpful unless you really want to visualize the retail store, but I would recommend trying to identify your variables and write any rates that are given as derivatives of those variables. So pause the video for just a moment and see how much of that information you can organize on your own. So we have weekly sales cost, which is S. So the sales, not cost, excuse me, just the weekly sales. And the weekly advertising cost X. Here in this case, they are both in dollars. And they're related by this function, this equation that we'll be using later on. It says the store is currently spending $2,000 per week. That's how much we're spending on our advertising costs. So that means X is equal to $2,000 right now. And they decide to increase the advertising budget by $300 per week. So we're going to need to know what is ds over dt and what is dx over dt. This increasing the advertising budget by $300 per week. Well, X was our advertising costs. We're increasing that, so that means dx over dt will be a positive $300. I want to find the rate of change of sales. So in other words, I'm looking for ds over dt. So I'm going to try to find that. Now notice here, we weren't given a value for S. We weren't given a value for our total weekly sales currently. And you could actually go and find that number if you wanted. If you wanted to, you could use the equation that was given to us. S equals 50,000 minus 20,000 times e to the negative 0.00004x. We could just take x equals 2,000, plug it into our equation, and then solve for s. However, I'm going to show you that we don't always need every single piece of information. We can actually solve this problem without knowing what s is. So I've got my variables, I've got my derivative, I've got my equation. My next step then would be to take the derivative of this equation with respect to time t. So I want to take the derivative with respect to t. On that left-hand side, the derivative of s, well, that's just going to be 1, but s is a function of time, so that means I need to multiply that by ds over dt. So you can either have 1 times ds over dt or just ds over dt. 50,000, this is a constant, so its derivative will be just 0. Here, this part we want to be really careful with. We've got negative 20,000 times e to the negative 0.00004x power. Here we actually have a chain rule. Remember, for the chain rule, when we're dealing with exponentials, e to some function of x in this case, we're just going to multiply that exponential function by the derivative of our power. So negative 20,000, first of all, this is just a constant multiple, which means it just comes down to our next step. Negative 20,000 times the derivative of our power. Well, here in this case, the derivative of our power negative 0.00004x will just be negative 0.00004. almost, but remember, we're taking the derivative of x. X is a function of time. It changes as time goes on. So that means that I need to use implicit differentiation, which means I need to multiply this by dx over dt. Times, and then the exponential part of this problem stays exactly the same. We're still going to have e to the negative 0.00004 x power. So here is my derivative. You can sort of think about this as our u prime times e to the u for our chain rule, if you need to go back and review that. But here is our derivative. I'm going to clean this up just a little bit here. I'm going to take negative 20,000 times negative 0.000004. So let me make sure I'm careful with all of our decimal places. I end up with ds over dt is equal to, in this case, positive 0.8 e, oops, and I forgot my dx over dt. We can't forget that. So 0.8 times dx over dt times e to the negative 0.00004 x power. And so now at this point, this is our derivative. We've simplified it as much as we can. If I go back and look at what I started this problem with, we said x was equal to 2,000, so we can plug that in for x. We said dx over dt is equal to 300. We can plug that in for our derivative. And we're solving for ds over dt. That's what we're trying to find. So ds over dt is equal to 0.8 times dx over dt. I've already forgotten what that is. We said that was 300 times e to the negative 0.00004 times x. Our x value was 2,000. So times 2,000. So here again, just be careful with your decimals. I've got 0.8 times 300 times e to the negative 0.00004 times 2,000 power. I end up with ds over dt is equal to 221.55 if I round to 2 decimal places, since we're working with dollars and cents here. So I also want to give a unit with my answer. So first of all, the unit on S, remember S is sales. If we go back and look at our problem here, we had weekly sales S, which was measured in dollars. So first of all, $221.55, we'll say, here I'm going to write it out as dollars per, what is my unit of time? What is dt? Well, t was measured in, here in this case, per week. Per week. Our current unit of time would be week. So in this case, if I wanted to talk about what this number means, if you're just giving your answer on MyMathLab, you could say $221.55 per week. But if I want to talk about what this number means within the context of the problem, we can say that the weekly sales will increase, and we know that it's going to increase because we ended up with a positive number. Will increase by $221.55 per week. This is the impact of increasing our advertising budget on our weekly sales.